let's go ahead and get started. So let's see. So what did we do last time? So last time we looked at Riemann sums. And they were ways to approximate areas below curves. And it's important to note this does not usually find the exact value, just an approximation. So what we want to do is so the goal, let's say, is to find a way to determine the exact area for the basic classes of functions that we study. So what are those basic classes of functions? There's really just three of them. Let's say polynomial functions, and in parentheses, I'll put rational functions because we'll also look at those a bit. They're not the same kind of functions, but right, rational functions, right, these are ratios of polynomials. We'll also look at the exponential functions. And we'll look at their inverses, the logarithmic. And that's pretty much all we look at in this course, again, versus an engineering calculus sequence. There's one big class of functions missing, namely the trigonometric functions. So the first thing we want to talk about is the antiderivative. That's what this section is called. So let's define an antiderivative and then think about what example might be. So an antiderivative of a function let's say little f of x is a function I think I should have commas here. Capital F of x such that when you take the derivative of this big function, you get exactly the lowercase f of x. Okay, so it's not just taking the derivative, it's thinking of a function such that when you take the derivative, you actually get the function in question. So in some sense, it's really going backwards, if that makes sense. So, right, maybe if we do like a diagram, that would help. So, for example, if you have this f of x and you take the derivative, you would get this little f of x, and then, if you take the derivative of this thing, you would get f prime of x, right? So this is the function. This is the antiderivative with respect to f of x, so it's the antiderivative of f of x. And then down here, this would be the first derivative of f of x. So hopefully that'll keep things straight for you. So let's think of a concrete example. So example. What is an antiderivative of, let's say x squared? Okay, now keep in mind, the derivative of x squared would be 2x. We're not trying to think of the derivative. We're trying to think of some function such that when you take the derivative, you are left with x squared, if that makes sense. Okay, does anyone have any guess there for me? Anybody want to take a gamble at what the derivative of x squared is? 2x. So 2x is the first derivative. So you're going downward. You're still thinking derivative. You need to think of something else. So in general, when you take the derivatives of polynomials, the degree is getting lower, right? So if you're doing antiderivatives, you want to think about going backwards. Yeah, so that's a good guess there, 1/2 x cubed. So let's take a look at that guess. Let's investigate that. So the first guess we got, 1/2 x cubed. So the way we could check is we could take its derivative. And if you take the derivative and end up with x squared, you did the right thing. So if we take the derivative of this, we would get 1/2 times 3 times x squared. So we would get 3/2 x squared. So the x squared part's coming in there, but we've got the wrong coefficient. So this was incorrect, right? Because we have a 3/2 in front instead of just a regular coefficient of 1. So 1/2 was close, but what we really want is a 1/3 to cancel out with a 3. So now we know what the right answer is. So we could guess, I guess, write another guess. Say, okay, 1/3 x cubed. And then this one does check out because we take the derivative and we get 1/3 times 3 now times our x squared, and we're just left with x squared. So this one checks out. So 1/3 x cubed is an antiderivative of x squared. So then it begs the question, my analysis professor in graduate school got me addicted to labeling things. So if I'm over labeling, sorry if it's mildly annoying. All right, so what is the question? Is 1/3 x cubed the only antiderivative? Writing. So we're asking, is the antiderivative unique with respect to the function in question, x squared? So what do we think? Do we think that this is unique? So it's really just a yes or no. I guess we could, how do we set up a poll? Switch to desktop app. Yeah, I can't do polls on here, unfortunately. I have to download it, but then I gotta go to IT and all that stuff. So I just use it through the browser. I could set up Socrative to do it, but it's too much work. So If you think it's unique, just type yes in chat. If you think it's not unique, type no. I'm just trying to get a sense of what people think. If it's unique, if it's not unique. If it's not unique, can you think of another one? So I'll tell you the answer. The answer is no. The antiderivative is not unique. So the question then becomes, what is another antiderivative? Well, you could really add any constant to this, and the reason is if you take the derivative of any constant, it just vanishes, right? It becomes zero. So adding any constant to 1/3 x cubed would not affect the value of its derivative. So for that reason, we would call 1/3 x cubed plus, usually they do like a capital C, the general antiderivative. Or the family of antiderivatives. I think your textbook's going to use general antiderivative more, so I'll just underline that one. Okay, so let's try to think of some more examples of antiderivatives quickly, and then from there, we'll see if we can postulate a rule for the class of polynomial functions. So example, find the general antiderivative of each function. Yeah, I don't know if I should capitalize general antiderivative every time or just when I define it. I don't know. I've been studying some German lately, so it makes me want to capitalize every noun. So I apologize for that. Okay, so let me give you a handful, and then maybe I can try and mess around with the breakout groups and see if that does something. So let's say, I don't know, let's say little f of x is let's say 15. B, let's say g of x is 8x. C, maybe h of x is 12x to the fifth. And D, maybe we have one more. Say p of x is 11 minus an x cubed. So let's try those four functions. Let me see if I can. Didn't get all of that. Can you scroll back up for a bit? Oh, I got a bunch of no's, so that's good. Well, this is where I'm at right now. Again, I'll post these notes, so if you didn't get it. I was just going to see if I could figure out how to do how can I do this? Enable breakout sessions. I've never tried this before. All right, let's try breakout session. If it's 13 sessions, automatically participants per session. Oh, we want 4 sessions. Does that make sense? Let's see if this works. I just want to try and break you guys into smaller groups so you can talk about these 4. Just see if it works. If it doesn't, then we'll see. So, okay, 0, 1, 2, 3, 4. Okay, so it did a good job. So I'm going to start these breakout sessions. And I'll just let you chat with each other for 2 or 3 minutes and then postulate what your antiderivative for each one is. So again, this first group, Casey, Kelsey, Matt, and Sean, you will be doing A. Anthony, Justin, Morgan, you'll be doing B. Christopher, Kelsey, Riley, you'll be doing C. And the fourth one, Blake, Jason, Vaughn, you'll be doing part D. Does that make sense? So I'm going to go ahead and start these, and then I'll put up this again. So we'll see if this works. Again, part A is f of x is 15. You want to find the antiderivative. Part B, g of x is 8x. You want to find the antiderivative. Part C, h of x is 12x to the 5th power. And part D, p of x is 11 minus 9x cubed. So I'll set the timer for 2 minutes or something, and then from there, I'll try and see what people have as an answer. Okay, so does anyone have any answers from the breakout sessions? Let me go ahead and join. Okay. So we did kind of get one piece of the puzzle a little bit wrong. Remember, for each of these, if we're doing the general antiderivative, they should all have a plus C with them. So actually, for all of these, we need a plus capital C. That would be the general antiderivative, or the family of antiderivatives. So I'm just going to add a plus C to all 4 of these.
Professor?
Yes.
Are you sharing your screen right now?
Oh, did it stop sharing? It probably did because of the breakouts or something.
Okay.
Let me go ahead and share again. It says I'm sharing my screen. Are people not seeing it?
Oh, no, I can't see it. I don't know.
I don't see it.
All right, I'll stop
I
it and
cannot
start
see
it
it.
again. It says I'm sharing, but clearly people aren't seeing it, so it's not good. Stop sharing. That's not good. It's not letting me do anything here. Do close it down. Did these? I don't know what's going on. It's not letting me share for some reason. All right. Well, I guess what I'm going to do is I'm just going to assign a host, leave the meeting, and then come back. That way I can restart my browser. Does that make sense?
Yeah, it makes sense.
All right. So I'm going to do that because I can't. It doesn't seem to be working any other way. So. Okay, so I'm back. So I don't know if the recording is still going, so that's great news. I was worried it was going to be 2 pieces. All right, so let me share my screen again. All right. Can everyone see it now?
Yes.
Yeah.
Okay, good. All right, so let's go back. Okay, so that's all I was saying before was for all of these 4 that we did in the breakout meetings, we had to add a plus C to it. So now we're trying to write down rules. So I'm starting with rule number 3 because there's 2 special cases that we kind of saw. So the main idea, though, is this rule number 3. So if f of x is just a regular polynomial term like x to the n, then capital F of x, which is x to the n plus 1 divided by n plus 1 plus a constant, is the general antiderivative. Okay, so that's the main rule we were utilizing up there. Add 1 to the power, then divide by that. And you can contrast that kind of to the derivative. The derivative, you bring the number down to multiply, and then you'd subtract 1 for the power. So this is exactly the opposite. You add 1 to the power first, and then divide by that. The 2 special cases, well, one we didn't quite look at. The second one we did. So let's say if, so this is kind of like a polynomial, but we're not really using this rule. But let's say if f of x is just some constant, let's say k, then the antiderivative, capital F of x, would be kx plus c for k, a constant. So that's like part A and part D. When you were doing the antiderivative C and D, the first term here, 11, it became 11x. Now, one we didn't look at but will also occasionally come up. Let's suppose that your function was actually not a general constant, but let's say 0, specifically 0. Well, the only things that have derivative equal to 0 are regular constants. So if you were trying to take the antiderivative of 0, then your antiderivative in this case would just be a constant c. Okay, so those are kind of the rules we have so far. Let me just do 2 more examples, but I think everyone probably has the hang of it. Example. And let me use some notation too. Let's introduce some notation, then do an example, because generally they don't say, right, it's kind of wordy to say, okay, here's this function, find the general antiderivative. So the integral notation we were using with Riemann sums that meant find an area also mean find an antiderivative. And you can probably guess the connection coming that these antiderivatives are going to allow us to predict the areas below curves. We're not quite there yet. We'll probably get there on Friday. But let's talk about the notation. So the indefinite integral of a function, say f of x, is written that elongated s with an f of x in the inside, and then the end is a dx. And one way to think about it is we can say this means find the general antiderivative of f of x. So if you see, right, just e.g., one way we could have written the very first example we did, we could have this integral of x squared dx, and that would just be 1/3 x cubed plus c. So now we don't have all those words. It's a way to compact the instruction set. A lot of mathematical notation is just used to kind of indicate, to make things more efficient when writing. Okay, so let's do 2 more examples using those rules. So example, and we'll just say compute. So A, let's say I'm finding the integral of 15x squared plus 10x minus 9 dx. So we just use the rule on each of the 3 terms. So we would have 15x to the third, then divide by a 3, plus a 10x squared over a 2, and then minus 9x. And then add our constant on. Again, the first 2 terms, I'm using that third rule. And for the minus 9, I'm using the second rule, which just says tack an x onto a regular constant. Again, 15 over 3 is just 5, so this is 5x cubed plus 5x squared minus 9x plus a constant. Part B, maybe we have a rational function, something like 8x squared minus 5x over x dx. Okay, so the thing here is you might say, oh, I'll just go to the top and do the antiderivative of 8x squared minus 5x, and then go to the bottom and do the antiderivative of x, and then that's the antiderivative. Well, it doesn't work that way. Remember, the derivative played nice with add and subtract. It kind of worked the way as expected, but if you wanted to find the derivative of 2 functions that were multiplied or 2 functions that were divided, we had special rules. Well, the same is going to be true with antiderivatives. We're going to have special rules to deal with multiplication and division, and we're not there yet. But we can simplify what's inside the parentheses first and go ahead and rewrite that rational function using the common denominator and simplify. So again, algebra is our friend here, and we're going to go ahead and use some algebra to simplify before we do any integration, right? So 8x squared, I can write that over x, and then I can subtract 5x over x. This is just using your common denominator trick from arithmetic. And then we can simplify what's inside the integral, so then we're just integrating 8x minus 5. And now those are two simple things to integrate. So again, we're going to have 8x squared over 2 minus 5x plus a constant. So we have 4x squared minus 5x plus a constant. And that is the antiderivative there. So let me see. So we got to start on. So let's just remark that about the addition subtraction. Mark. Antiderivatives. Function behave well or behave regularly. With addition, subtraction. However, multiplication, division will require more advanced techniques. So basically, if we want to rewrite this, we could maybe call this a proposition. So suppose f of x and g of x are continuous functions. Then one, the integral of f of x plus g of x dx, you can do each one separately. And when we're working term by term, that's exactly what we're doing. So when you looked at part D, and I'll do it again with subtraction, even though it's not really necessary. So when you look at, let's say part A previously, 15x squared plus 10x minus 9. What did I do? Well, I used the antiderivative rule on each part. That's what this new theorem is telling us. It's telling us that we're allowed to work piece by piece when things are added or subtracted. But you know, if you had two things that were multiplied together, f of x times g of x, it's not going to be as simple as doing something like this. That is not true. And it's also not true with division. So in the very last example where we had something being divided by something else, you can't just go ahead and try and integrate the top and integrate the bottom. So that's what I mean when I say the integral does not behave this way. You don't have such rules. So do not attempt. You're just usually going to get a wrong answer. So we're going to learn basically a few techniques in this class. The techniques of integration, once we get the basics of antiderivatives down, are integration by use substitution, integration by parts, and integration by partial fractions. And, they deal with these in various ways. Okay, so probably this is a good place to stop. We'll do a few more polynomials, but then next time we will jump into exponential functions and logarithmic functions, and then we'll have all the basic antiderivatives down, and then that's what the homework also will test you on. So, okay, why don't we stop here, and then I'll ask if there's any questions. And I know a few people want to talk to me after class, so let me answer some questions if there are any.
Sorry.
Yeah, go ahead.
I don't know if like other people to go first since mine's personal, but
Yeah. Let's just hold off on yours. Let's just hold off on yours for a second, and I just wonder if anyone has any questions on the section. I want to wait for them, and then once everybody leaves, then we can talk about your issue. All right. Thanks, Sam. Okay. So if you don't have any questions, feel free to exit the meeting.
My question, slightly personal.
Okay, then we'll just wait on yours as well. All right, let me stop the recording.